Hello, good people of calculus. Mr. Klein here in a hat, which is fun. you know, this is true. I had no idea that I owned so many hats. Today, by the time we are done, check out this bad boy right here. The derivative of the integral from cosine of x to sine of x of t cubed dt. Today, by the time we're done, you're going to be able to do that problem in one step. Now, in order to get you there, we have to talk a little bit about inverses, about things that undo each other. Mathematical operations, pretty much all of them have inverses. So, for instance, for addition, the inverse would be subtraction, right? If I give you $5 and then I take away $5, you're right back where you began. Likewise, we've got multiplication and division. If I double your money and then I cut it in half, you're right back where you started. Finally, we've got like squaring and square rooting. They also undo each other. So the question for today is the derivative and the integral. Are they inverses? Let's find out. Well, let's begin here. We want to take the derivative of, by the way, I'm giving you a simpler problem than this to begin with. This one's kind of high powered. Let's begin with one that we can do by hand. So this says, take the derivative of the integral from 1 to x of cosine of t dt. We're going to do this in two steps. First step is to evaluate the inside. So we're not going to deal with the derivative part just yet. So we would take the antiderivative of cosine. We think to ourselves, what function, if you take its derivative, do you get cosine? The answer is sine. Okay, so we get that. Then the next step would be, fundamental theorem tells us to plug in the x, plug in the 1, and subtract them. So we would get the derivative of sine of x minus the sine of 1. And then we need to take the derivative of this. Let's take it in parts. First part, the derivative of sine of x is the cosine of x minus the derivative of the sine of 1. Wait, the sine of 1 is a number. And I know the derivative of a number is 0. So this just gives us this. Huh. Interesting, right? I think I might see a pattern. Let's do another problem. Okay, this one's a little bit different because this time, rather than having just x in the upper limit, this time we have 5x. Let's see if that changes anything. So same game, take the derivative of the inside function, or the antiderivative of the inside function, the integrand. So let's see, what function, if you take its derivative, do you get sine? Is that cosine of u? No, it needs a negative. Negatives cancel. Yeah, good. 5x to 3. Now let's plug in the 5x and the 3. Minus negative cosine of 3. All right, and our last step will be to take the derivative of what we have on the inside. So the derivative of the negative cosine of 5x would be a chain rule problem. Outside function is negative cosine. Derivative of negative cosine is sine. Leave the inside function alone and multiply by the derivative of the inside. Plus the derivative of cosine of 3 is 0. So this expression is equal to this. Huh. Huh. Hmm. Do you see a pattern? Do you see what's going to happen? If you do, think about what the answer to this one should be before we evaluate it. And here we go. I'm going to go just a little bit faster because I think we've kind of got the idea now. I take the antiderivative of e to the t, the integrand. You get the same thing back. Now this one's kind of interesting, right? Because the upper and the lower bounds both have x in them, and so we're thinking about is that gonna change things at all? Well, let's see. E to the x cubed minus e to the 2x. Now let's take the derivative. This time we're going to have two separate chain rules. Here's your first one, here's your second one. First one, by chain rule, would be e to the x cubed times 3x squared minus, second one, e to the 2x multiplied by 2. Huh. Hopefully you see a pattern that works here and here and here. And this is my challenge to you. Can you write a formula for the derivative of the integral where the upper and lower bounds are functions and your integrand is f of t? And I'll even give you a hint that the answer is going to look something like this. Pause the video for a second. See if you can write that on your own. And then when you're done, unpause and you'll find out if you're right or not. Okay, so I'm going to assume that you've tried it on your own. The pattern goes a little something like this. The function that is in the integrand, the inverses cancel each other out, the integral and the derivative, which is why if you look back at the last three examples, this function and this function are the same. This function and this function are the same. This function and these functions are the same. Therefore, this should say f of something and f of something. If you got that, good. Second component goes like this. You should have the upper limit as your first inner function multiplied by its derivative. And that happened because of the chain rule. Second part should have the lower limit function as your inner function multiplied by its derivative. So there it is. There's the formula. If you were able to come up with that on your own, give yourself a little pat on the back. Nice work. Let's note that we can now use that to evaluate this expression right here. I know that the result is going to be something times something minus something times something. That would be a good start. Hey, this is another case where if you want to try it on your own and pause the video and then come back and watch me, that's probably a good idea. All right, let's see. So now this is t to the third. So I know that this function will be something to the third. This function will be something to the third. The upper bound is sine of x, so this will be sine of x and derivative of sine of x. And then the lower bound is cosine of x. So inner function cosine times derivative of cosine is negative sine. There's your answer. If you got that, nice work. Hey, just a fun fact. If you factor this out, you get sine of x times cosine of x, right? Because both terms have a sine and a cosine they can pull out. And what you're left with is a sine squared from this one. Because of the double negative, you get a plus, and then you're left with a cosine squared from this one. So the answer to this actually ends up being pretty simple because the sine squared plus cosine squared is one of our Pythagorean identities. It's equal to 1, and it cancels. So we're left with sine of x times cosine of x. Cool. Okay, so how do we use this? Well, we use this because it is related to integral functions. So check this out. Here's a type of integral function that you have not seen before. This time, rather than your upper bound being something simple like x, your upper bound is going to be x cubed. And what that means is that if you are asked for, I'm going to write it over here, the derivative of this function, that would be asking you to do d dx of the integral from 1 to x cubed of f of t dt. Oh, Mr. Klein, I see it right there. It's the derivative of the integral. So we're using this formula that we cooked up right here. All right, so what does it say? It says that you got to leave the function alone. So we'll have f of something, and that something would be x cubed multiplied by the derivative of x cubed, which is 3x squared. Now, if you haven't already figured it out, you don't need to do anything with one of the bounds if it is a whole number. And I'm going to show you why. If you don't care why, skip the video or skip this part. The reason that you don't need it is that this would be f of 1 multiplied by the derivative of 1. And since 1 is a constant, the derivative is 0. And that right there, that 0, that'll be true anytime one of the bounds is a constant. And so that bound will just kind of disappear. So we're left with, this is the equation of the derivative. All right, so let's use those two facts. We're asked to do two things. The first is to determine g of 2. Now, when you find g of 2, that just means plug 2 in. So that would be the integral from 1 to 8 of f of t dt. That's a regular old integral. We would come up here. We would say, here's 1. Here is 8. So I see an area that's below the curve right here that has a value of -1. I see an area that is above the curve right here, above the x-axis. And that's going to have an area of pi times 2 squared, cut in half because it's a semicircle. And then you've got this little region right here, which has an area of 1, 2, 3 times 2. So this has an area of 6. It's above the axis. So our answer is going to be -1 plus 2 pi plus 6. You could clean that up to 5 plus 2 pi. Okay, now, for whatever reason, I accidentally cut this off. But the other thing I wanted you to do is to determine g prime of 2. And to do that, you're plugging 2 in right here. So what would that look like? F of 2 cubed minus 3 times 2 squared. So it will be f of 8 multiplied by 12. F of 8, you are going to locate up here. At 8, the value of the function is 3. Therefore, this is going to be 3 times 12, which gives us 36, one of my favorite numbers. Okay, so that's enough for today's lesson. There's some problems in section 6-2 of the book that I'd like you to take a look at.